Alright, Logic fans, what's up? It's Ash. Here we're going to hit section 6.10 of the text, our 10th section on quantificational syntax, and here we're going to explore theorems, our second section on theorems. In particular, we're going to be focused on proving theorems of logic that involve relations. We do not treat identity in this section. That is preserved for a later section. So if you're looking or interested in theorems of logic involving identity and relations, be sure to check out the later sections of the text in these later videos. But we do presuppose that you're familiar with the methods of proving theorems in quantificational context as explored earlier in the text. So if you're not comfortable with that, make sure you check that out now. All right, let's rock. All right, so let's go ahead and look at our first example of a theorem involving relations. And in this case, right, since you're proving a theorem, you have to find either an assumption you can make, or else you have to find an instance of an axiom that you would like to invoke. So if you want, you can go ahead and try to reverse engineer this, and that could give you a clue as to which assumption or which axiom to invoke. Or if you feel like you can solve the problem, just go ahead and solve it. But either way, pause now and see if you can't crack this one. Okay, here's a quick hint. So if you're having trouble, just remember you can reverse engineer it, right? So pretending that you have the theorem available, if you strip it of its quantifiers using universal instantiation, it would look something like this. And now you can see, aha, look at this. I've got a really, really nice recognizable axiom. So maybe in this case I should start with an axiom, pause now, and solve from there. Alright, and it's not that bad, right? So first you just invoke your axiom, LEM, which got you this, and then we just need to reverse, from this back up to this, which is the desired theorem, which we can do instead of universally instantiating, we universally generalize to that, and boom, there's our proof that this sentence is in fact a theorem of logic. And just look at what it says. For any x you pick out of Santa's bag, either it bears the relation R to itself, or it's not the case that it bears the relation R to itself. And that absolutely should remind you of the law of the excluded middle. So this is a purely logical feature of relations. Let's check out another example. Alright, so let's take a look at this case. Here we have an interesting feature of relations, right? So it's a theorem that this is logically equivalent to this. In other words, the order of the quantifiers doesn't matter, provided you preserve the order of the relata accordingly. So if you have x out front here and you have x in the first relata position here, the same thing is going to work if you have y out front and y in the first position here. So if you want, you can reverse engineer. Note that it's a biconditional, which suggests we should be using CP twice, and that's in fact what we're going to do. So pause now and see if you can't prove that this big sentence here is a theorem of logic. Alright, hopefully you were able to get it, and it's not that bad. So if we picture this as sort of equived apart, right, then you're going to get two conditionals, the left to right, this, if this, then this, and if this, then that. So proving the left to right direction first, we assume this, and we look for what's on the right-hand side there, and it's a fairly straightforward way to get it, just as long as you build, strip apart your quantifiers and build them up properly. You're going to be able to accomplish it. And it's the same thing moving the other direction, and it just basically follows the typical format of a biconditional proof, right? Which is to prove two conditionals using CP, conjoin them together, and then equiv back to the desired form. Alright, let's keep exploring some of these theorems of relations. Okay, let's take a look at this case, and unlike in the last example where we had two universal quantifiers, this time we explore the possibility of what if you mix them. So if you have a universal and an existential, but you preserve, the lead quantifier's position in the relata, here, x in the lead, and here x first, here y in the lead, and here y first. Does that hold? And indeed it does. So you're actually in a position to be able to prove this now. And if you weren't able to crack the last one, see if you can't crack this one, albeit just sort of modeling yourself after the previous example. Pause now. So hopefully you're able to get it, and again, this is just a biconditional, so you're going to prove the left to right direction using CP, then you're going to prove the left to right direction using CP, then the right to left direction using CP. The order there doesn't matter. Conjoin them together and equiv to this thing, and that's what we've done here. So starting with proving the left to right direction, we assume this and look for this, and then it's just a matter of deconstructing this in such a way that you can build the desired thing back from it. So you want to make sure that you instantiate the right way to sort of signify where you're going to put things. And that's what we've done here. So model yourself after this very, very closely. Okay. Once you've obtained what you wanted, you go ahead and discharge the assumption, and you get the thing you assumed. Arrow the last thing you got, or the thing that you wanted here, and then you're off to prove the right to left direction, and it's a very similar procedure. However, there is one nuance. Since we've already used the existential pseudonym V up here, we cannot use it again here, right? So remember, existential instantiation carries the proviso that you can invoke an existential pseudonym provided that pseudonym has not been invoked on a previous line. In this case, it has, and it doesn't matter that it occurs within the scope of an assumption. It occurs on a previous line. So we got to make sure we go to a different one, and we want to avoid troubles that can occur logically if we help ourselves to the same one. So with that nuance, the problem very much mirrors the previous one. And yeah, you're just equiving back to the desired theorem, and it's interesting, right? So even if we have mixed quantifiers, a similar result to the last one still holds. All right, let's keep checking these out. All right, let's go ahead and try this example, and here's an interesting result that for all x, for all y, rxy is sort of logically equivalent to it's not the case that at least one x for at least one y, it's not the case that rxy. So this sentence here turns out to be logically equivalent to this sentence here, and remember we defined that in section 6.8, right? You can prove that two sentences, in this case this one and this one, are logically equivalent by showing that it's a theorem of logic that the one tribar the other. So that's sort of what we're doing here, and you get these interesting things. So these sentences sort of from a purely logical point of view have the same content. Let's go ahead and see if we can't prove this. You can go ahead and use the proving two conditionals technique. There's also a slight variation on this one that is helpful, and I'll show you that. But however you want to do it, go ahead and pause. Reverse engineering is always welcome. And pause now and try this one. So hopefully you've had a chance to get it, and if you wanted to do it the traditional, 2CP way, that's absolutely fine. It will lead to the answer. Here, I'm going to introduce to you a slightly different technique, which you can keep in mind for solving problems that your professor might confront you with. And basically what I've noticed here is that I can sort of get from this to this using QN. So if you just reverse engineer this, right, if you have for all x, for all y, rxy available, you can sort of double negate and use QN to come up with this. Similarly, you can go from this to this just using QN. So what I did here was a sort of more advanced idea, and it's good that you get some exposure to it. But what I did was I assumed for all xy, rxy, and I wanted to get that out of it, right? Now I'll show you why. So rather than just closing off immediately, I just used two double negations really quick. So I assume this thing, I want this thing, so I double negate it, and boom, there it is. And now I've got for all xy, if rxy, then for all xy, rxy. And that, of course, is a theorem as well. But now we can do a really, really nifty thing. All we have to do now is double negate 4 here and then undouble negate it immediately to get 6 so that we have the same line in two places. Well, what's the point? We can conjoin them together, and then we get using equiv, we get for all xy, rxy, if and only if for all x, for all y, rxy, right? And so that's a theorem, of course. But now we can just go ahead and use double negation and QN because those are rules of replacement to just sort of manipulate the right-hand side here into the desired form here, and so that's a whole other different way of getting it, and it's a really nice trick of the trade to keep in mind. But any kind of problem solving skills you want to bring to bear are more than welcome, and hopefully you've learned a few new ideas on how to problem solve and how to get desired results from these videos. Okay, let's keep it rolling. Alright, so for our final example, I want to look at one that's a bit harder. Alright, so here you have, it's another biconditional, but it's an interesting feature of relations. You got the quantifiers on the outside here, but here you've got one quantifier on the outside and one quantifier on the inside. So reverse engineering can really play an important role here, because you're going to have to think about, after you've assumed this, and stripped off the quantifiers, how to properly build this construction. Right, and you're going to have to think about, how to take the quantifiers off of this in order to build this particular case. So what I want to do here is, if you need it, is give you this hint. Okay, so let's assume that you assumed this, so you have it available here. All right, so that was like an assumption, and now of course you're looking for this guy. If you strip the quantifiers off of it, you end up with an expression like if fu, then ru, you won. Okay, it looks something like that. Now the question is from this thing, how do I build something like this? Okay, and so go ahead now and just see, we're just doing scratch work here. We're not doing our official proof yet. Can you figure out how to build, this sucker from this thing? And, it might help to just reverse engineer this on some scratch paper, but see if you can't figure it out. Pause now. Okay, so hopefully you've had a chance to think on it, but you've got this thing. And the question is how are you going to get this from this with the quantifier in here, right? Well, here's the trick, all right? Assume fu, right? And after you assume fu, you can get ru1 all by itself from modus ponens on this and this, right? And now that you've got that, you can universally generalize it, and you've got this. Then you discharge this assumption, and you get if fu, then for all y, ruy, which is really, really nice, right? And then, of course, you can just universally generalize this thing to get this construction, and then you've found this thing, and you're ready to go from the right to the left. So noticing this pretty complex way of building the inner quantifier, okay? This is how it's done. See if you can pause now and complete the proof that this is a theorem of logic. Pause now. Okay, so hopefully you've been able to figure it out. So we've got our biconditional. Okay, so we're going to assume this and then look for this guy. So we assume this, and we're looking for the consequent here. And we strip this of the quantifiers, and we end up with this expression. Then we use our little trick of assuming fu, using modus ponens to get this out, building the inner one, closing out so that we get this expression, and then universally generalizing this expression to get that, which is what we wanted. So we discharge that assumption. We write down the first thing we assumed, arrow, the last thing we got, which was this, the desired theorem, and now we've got our left to right direction. Now for the right to left, which I did not give you hints about, but you're going to assume this and look for this. So you assume it, and this is what you're looking for now, the right to left direction. So you go fu, right? And now you have a problem. You want to instantiate this, but you can't because this is a conditional. Use the same little trick. Assume fu, get the consequent out, strip it down, close it out, build with the y first, then the x, because that's what you're trying to build, okay? And then close it out, and the rest is just the typical CP, double CP proof of a biconditional. And that's one of the harder ones you'll find. So remember this little trick for building inner quantifiers on problems like this. There's plenty of such practice problems in the rest of the text. Be sure you're talking to your professor about these kinds of examples, these more difficult ones, and check out the problems in the text that ask you to articulate your own theorems of logic regarding relations and prove them, so you have a chance to design, test your own intuitions about what might be a theorem of logic with relations, and then of course be able to prove it. All right, logic fans, we'll catch you on the next video.